Good morning. In the last lecture, we almost finished the definition of the semantics of Haskell programs. And what we did was we looked at a very easy special case. We looked at so-called simple Haskell programs. So basically, simple Haskell programs are Haskell programs without pattern matching, and there were some other restrictions. And we will see how hard these restrictions are later on. Now, let's recapitulate what we defined, and we recapitulate this in a formal definition. So this is the formal definition of the semantics. It's the semantics of simple Haskell programs. Of simple Haskell programs. Well, maybe we can. And I don't know how easy this is. So what we have is we have a simple Haskell program. Simple Haskell means the program contains only one single declaration, and it's a declaration of a pattern, not of a function. So it's something without arguments. So let DOM be the domain of our program. Let DOM be the domain of a simple Haskell program. And since it only contains one declaration, let's write it down how it looks like. So let var equals exp be the only declaration of the program. So for example, this can be something like fact equals, and then we have an expression starting with lambda x, and that's the definition of the factorial function. So let this be the declaration of the program, and let exp be the set of all simple Haskell expressions. So all expressions that you may have in simple Haskell programs. Of all simple Haskell expressions. And then the function val, which maps every expression to a value, goes from exp to DOM. But not only that, we also have to take the environment into account. And the environment tells us for every variable what the value of this variable should be. So what we do is we define the function val. And now val goes from, it takes an expression, it takes an environment, which tells us what the meaning of the variables is, and then it gives us an element of DOM. And the requirement is that this environment has to be defined on all three variables of the expression, which assigns a value to every expression x and environment rho, where rho has to be defined on all three variables of the expression, so it has to be defined on 3 of exp. Now, we are interested in the semantics of an expression within a program. So our program has only one single declaration, this one, and now we look at another expression, x prime, and we want to know the semantics of x prime in this program. Now, in order to avoid the handling of programs, what we do then is we consider this declaration as being local. And then instead of x prime, we consider the expression let, and then this declaration in x prime. So the semantics of another expression x prime with the free variables of x prime. They are either empty, so there are no free variables, or the only free variable that we may have is this variable that is defined in this program. And the variables that are predefined in Haskell. So, and predefined variables in Haskell. So, in this x prime, you may also have plus, or you may have map. So, things that are predefined in Haskell, and you may have this variable that is defined in our program. And then the semantics of x prime in this program is defined as the value of the expression where we make this program local. So let var equals exp in x prime. And what environment do we take? We take the initial environment, which tells us what the meaning of the predefined variables is. And so in x prime we have predefined variables, and here the environment tells us what the meaning is. And we may also have this var, and here we have this definition of var locally, and then we know what the meaning of var is. So here val is defined as follows. Okay, so how is it defined? Now let's recapitulate this from the last lecture. Now the definition goes by case analysis with respect to the grammar defining simple Haskell expressions. Now the easiest simple Haskell expression is just a variable. So, I don't know, can you read this, or should I switch off the slide? Maybe I switch off the slide and then it's a bit easier. Now I don't write it down here, but see the slide. So what are the possibilities? If we have a variable, now this is repetition from the last lecture. If we have a variable, then what is the value of this variable in this environment row? Well, if we want to know the semantics of a variable, that's what the environment row is good for, then the environment should tell us what the semantics is. So it's row of var. So in other words, if we want to know the semantics of x, well, then hopefully our environment is defined for x, and then the environment might tell us that the value of x is the number 5. Now, if we have a constructor of arity 0, so this should mean this is a constructor of arity 0. So this is a constructor which takes no arguments. So something like 0. And now the value or the semantics of this constructor is just the name of this constructor itself. But of course it has to be an element of DOM. So this is in the subset constructions 0. These are all the objects built with constructors of arity 0. And this again is a subset of DOM. And this makes clear that this is a marked version of this constructor which is in DOM. Now if we have constructors of higher arity, like we have it here, then what is the meaning here? Well, the meaning of this is a function. It's a function of arity n. So it waits, you can see this from this arity here. It's a function which waits for n arguments, and if it gets n arguments, it gives you back this tuple. So these are the n arguments of the function, and what the function does is it adds one more component, the name of this constructor. So, for example, if your constructor here is suck, a unary constructor, then the semantics would be a function which waits for another object, for example 0, and then it would give you back suck, 0. So basically this is a function which is like this constructor and then generates constructor ground terms which look like this. Now, what else do we have? We have tuples. So if we have an expression which is a tuple of n expressions, then what is the semantics? Well, we simply build the semantics of x1, of x2, of xn, and then the semantics is the tuple of these values. So This is simply the tuple consisting of the semantics of x1 and the semantics of xn. And for tuples with just one component, we make no difference whether it's a tuple or whether it's this component itself. So in Haskell, it makes no difference whether you have a tuple of one component or just the component. And that's what I wrote down here. So whether you write this or whether you write this is the same thing. Now, this is also what you know from your Haskell programming experience. If we have applications, so one expression is applied to another, then what do we do? This semantics is defined recursively. So whenever we have an expression which consists of several sub-expressions, then we define the semantics of this bigger expression in terms of the semantics of the sub-expressions. So let's assume we know what the semantics of x1 is and what the semantics of x2 is. The semantics of x1 should be a function. Otherwise, this is not well typed. So it should be some function f. And then the semantics of this composed expression is simply apply the semantics of x1 to the semantics of x2. So take the semantics of x1, which is f, and apply it to the semantics of x2. So this makes clear that if you write two expressions beside each other, then the semantics is function application. We have defined this here. Okay, now there are some more expressions possible in simple Haskell. The next one is the if expression. Now this looks complicated, but it is easy. The next one looks complicated and is complicated, but this one is easy. So what is the semantics of this? Well, the semantics is, again, we assume that you know the semantics of x1, x2, x3. So if the semantics of x1 is true, then the result is the semantics of x2. And if the semantics of x1 is false, then the result is the semantics of x3, and otherwise the semantics is bottom, is undefined. Now this defines the semantics of if then else, and that's the usual semantics that you would expect. Now we come to the most complicated case, and that's the let case. Now, if we have a let expression like this, then what do we do? Again, we assume that we know the semantics of x and of x prime. Now, basically what this means is this is almost the same as the expression x prime. The only difference is that we know a bit more about the variable var. Var is defined to be exp. So the value of this let expression should more or less be the value of x prime. The only difference is that the environment row is not quite the same anymore. It is the same almost everywhere except for var, because the only thing that changed is the meaning of var has changed because we now have this extra declaration. So this makes clear that the environment is still row, the only difference is for var. For var, we now have something different. Now, what do we have for var? What is the meaning of var? Now, at first sight, you might expect that the meaning of var should be the semantics of exp. Now, that's true if you have non-recursive declarations. But if you have recursive declarations, it's a bit more complicated, because if this is a recursive declaration, so if this var also occurs in exp, then we know what the meaning of this should be. The meaning is the meaning of var should be the smallest function which satisfies this equation. So in other words, it should be the smallest function, the smallest solution of this function f. And what f does is it simply takes the right-hand side of this declaration up here, but replaces var by d. So this is the function which maps the left-hand side of this declaration to the right-hand side. And a fixed point of this function is a function where the left-hand side and the right-hand side is the same. So it's a function where the var, this here and this here are identical, and we want the smallest such function. So this is the least fixed point of f. So let's maybe recapitulate this again with an example. So suppose our program, if our program is the factorial program, so it's fact equals lambda x, if x is less than or equal than 0, then 1, else fact of x minus 1 times x. Now, if this is our program and we want to know the meaning of the expression fact 3 in this program. So we're interested in the semantics of fact 3 in this program. Then what we do is, instead of regarding programs and expressions, we instead regard just one expression, but we make this declaration local. So the semantics of fact 3 in this program is by definition, this is the semantics of the following expression. Let fact equals lambda x, and now the same thing as above, in fact 3, and that we do in the initial environment. Now, what is this? Well, by definition, this is the semantics of fact 3 in almost the same environment, but not quite. So this is the initial environment, which only tells us what the predefined variables mean. But we cannot completely forget about this let declaration. So in this environment, fact has a special meaning. Fact is now the least fixed point of some function f. So here I called it f. Before I'd normally called this ff, but let me call it f to have it similar to the definition on the slide. Now, what is f? Now, f takes a function and gives us back a beta function. So what f essentially does is it takes one approximation to the factorial function and gives us back a beta approximation to the factorial function. So f of fact I will be fact I plus 1. But how do we get this? Well, by definition, this is the value of this right-hand side. So this right-hand side is lambda x. If x is less than or equal to 0, then 1, else fact of x minus 1 times x. Again, in the initial environment, but of course now we have this fact, and the question is, what is the meaning of fact? And that's exactly what this function is good for. So this function f takes another function d and maps it to a new function. This new function we get from the right-hand side, but at the point where we have the recursive call, we take d. So fact is replaced by d. Now let's write this down in a more readable way. So what does f of d do? So d is a function, and the result is again a function. So if we apply this to some x, then what will be the result? Well, if x is less than or equal to 0, the result will be 1. And otherwise, it will be d of x minus 1 times x. Otherwise. Now this we know because we know the semantics of if, we know the semantics of less than or equal, we know the semantics of 1 and of minus and of times. Minus, times, and all this stuff is predefined, so its semantics is given by this initial environment here. And what if means, yeah, we defined this up there already, so we know the semantics of the if construct. So what we can see is, if here we have an approximation to the factorial function, so d is probably fact 1, then here we get a better approximation to the factorial function. This will be fact 2. So this is exactly the function ff that we had before. So we called this ff before. And now, by our definition, if we have such a recursive declaration, then the meaning is the variable that is defined here recursively, its semantics should be the least fixed point of this higher order function. So it should be the least fixed point of this function ff, and now in this definition I call it f. So this is exactly the same thing that we had before. I just now wrote it down in a general way. And if you have a non-recursive definition, this works just as well. So for non-recursive definitions, so declarations where var does not appear in exp, then of course you might ask yourself, why do I need least fixed points here? And you don't need least fixed points here, but it doesn't matter. You can write, so there our idea was, why don't we just say var is, the meaning of var should be the meaning of exp. Now, this is exactly what will happen if we have no recursion. So let's see why this happens. So for non-recursive declarations, what happens for non-recursive declarations? Well, for non-recursive declarations, what would be the value of let var equals exp in x prime, in row, say? Well, it would be, again, the meaning of x prime in row plus, now the variable is replaced by the least fixed point of f, and f would be the meaning of exp in the same environment, but now the variable would be replaced by d. By definition. Now, if this is a non-recursive declaration, then this means the variable var does not occur in exp. Now, if the variable var does not occur in exp, then it is not very interesting what this environment does for var. So, this is the same as this. Since var does not occur in exp, if the definition is not recursive, so what is then the least fixed point of f? What is the least fixed point of f? In fact, what is the only fixed point of f? F only has one single fixed point. Now the thing is, this d only occurs here. Now when we drop this, then this d does not occur here at all. So, in other words, the result of f is always this, no matter what the argument is. If you have a non-recursive definition, then this d is completely irrelevant for the result of f. Now, if you have a constant function has only one fixed point. Fixed point means the argument is mapped to itself. Now, the only possibility to get a fixed point is to apply f to this. If you apply f to this, you get this back again. If you apply f to something else, you also get this back again, but then this is not identical to the argument. So the least fixed point of f is this. So this is the only fixed point, since d does not occur in val exp row. So in other words, here we could also write, instead of this, we can write val exp row. And this is exactly what you would expect for non-recursive definitions. So if this is a non-recursive declaration, then the semantics of this let expression is just the semantics of x prime. The only difference is that now the variable var is assigned the meaning of exp. Now that's what you would expect. This means var is now exp. And this is what's happening here. So we can use this formulation with the least fixed point for both recursive and non-recursive declarations. It works okay for non-recursive declarations as well. If you know that the thing is non-recursive, you can, of course, express it in a more easy way. But if it's recursive, you need this least fixed point. So this is not easy. I know that this is not easy, but the longer you work with it, the more you start understanding it. So when you see that the first time, it is problematic, but don't give up and try to understand it. That would be, it's not as difficult as it looks like. And now to, as a happy end, the last case, that's again easy, or quite easy. And that's the case where the expression is a lambda expression. So what should be the meaning of a lambda expression? Something of the form lambda var arrow exp. Now the meaning of this expression should be a function. It should be a function, and what should this function do? Well, it should take some argument, like var, and then give us back the meaning of exp. But of course, in this exp, this var might occur. So it should be a function like f. F takes some argument d, and the result is the meaning of exp in almost the same environment. The only difference is that, well, the argument of f, that should be the meaning of var. So it should be a function which maps d to the value of x, but here var has to be replaced by d. So the meaning of var is d. So let's make an example. So here's another example for the case with lambda. Let's look at what is the value of an expression like this. Lambda x goes to x plus y in an environment rho where rho of plus is the addition function, and now rho should be defined on all free variables of this expression. So the free variables are plus and y. X is not free because x is bound by this lambda here. So rho has to be defined on y as well, and let's say this is the number 2. So then what is the result? It's a function f. And what does f do? F takes some argument, and now this argument is the meaning of x. F takes the meaning of x and gives us back the meaning of x plus y. So it gives us back the value of x plus y. And how does the environment look like? Well, for y and for plus, everything is the same. So this rho will still map plus to the addition function and y to the number 2. But what happens with x? Well, for x, we now have to take the meaning d. So for x, we now take d. So this is the function which maps the meaning of x to the meaning of x plus y. Now, let's continue. What would this mean? Now, if we want to compute the value of this, by definition, what we do is we take the value of plus. So it's the value of plus, that's the addition function, applied to the value of x. Sorry. It's the... We take... Let me call this rho prime. Then what we do is we take the value of x and the value of y and apply the value of plus to it. So this is rho prime of plus applied to rho prime of x and a rho prime of y. So what is this? This is the addition function. What is this? This is d. And what is this? This is 2. So in other words, f of d, the result of this is d plus 2. So this is the function which takes a number d and returns d plus 2. And that's what you would expect. This expression here, the semantics of this should be the function which takes some number d and gives us d plus 2, because in this environment, the value of y is 2, and the value of plus is addition. So in this way, we have now defined the semantics of a full programming language, simple Haskell. Admittedly, this is a small subset of Haskell, but not a real restriction of Haskell, as we will see in a moment. And, well, you can see that on 2 pages, you can define the semantics of a real programming language where you have recursion and everything. And now this is formally defined. There's no, if someone implements a compiler or an interpreter, he knows exactly what to do because this defines this in an unambiguous way. And you can see this is not as complicated as you might guess. It's really just 2 pages. And so this is indeed doable. And that's something one should do when one defines a programming language, because then it's absolutely clear what the semantics should be. And we can also see that the semantics, for example, fixes things like lazy evaluation and stuff like that. Everything is fixed in these just 2 pages and in a very formal way. Okay, but as I said, this is just for simple Haskell, and simple Haskell is not quite full Haskell. The main difference between simple Haskell and full Haskell is simple Haskell has no pattern matching. And that's, of course, not so nice, because in reality, we would like to use pattern matching. And so the question is, how can we transform full Haskell programs into simple Haskell programs? And that's what we will do in the next subsection. Semantics of simple Haskell programs. Now we come to the semantics of complex Haskell programs. And instead of extending this definition to more constructs of Haskell, we instead present a transformation from complex Haskell programs to simple Haskell programs. And it's a transformation which works automatically. So you can immediately go on and implement this in your computer, and then every complex Haskell program will be automatically transformed into a simple Haskell program. And that has many advantages. So what we do is we define an automatic transformation from complex to simple Haskell. And this will be used for, well, it will be used to define the semantics, because we say the semantics of a complex Haskell program is simply the same as the semantics of the corresponding simple Haskell program. Corresponding means that's the simple Haskell program that you get from the transformation. So in this way, we can keep our semantics definition as it is. We just have this additional transformation, and then we can say, well, this transformation defines the semantics of complex Haskell in terms of simple Haskell. But since this transformation is automatic, we can also use it for the implementation of Haskell. So what we will do later on is we will show how to implement simple Haskell. We will not show how to implement complex Haskell, because if you want to implement complex Haskell, what you do is you first transform it automatically to simple Haskell, and then you can, so this is if you want to, first step of the compiler, this transforms complex programs into simple programs that are equivalent, and then we can discuss about how to implement simple Haskell. We will do this in chapter 3. And we will also use this for type checking. So if you want to do type checking for complex Haskell, then what you do is you first transform to simple Haskell, and I will tell you how to do type checking for simple Haskell, but not for complex Haskell. So for these 2 points, it's important that this transformation works automatically. So both these things here, automatability of the transformation is important. Okay. So, as I said, simple Haskell basically, let's put on the definition of simple Haskell again. This is basically the definition of simple Haskell. And as I said, the main restriction is we have no pattern matching. So the question is, how can we transform a program with pattern matching into a program without pattern matching? And to do this, we need some more predefined functions. So Haskell has some predefined functions like plus and minus and map and whatever. And we need some more. And these predefined functions we mainly need because then we can do without pattern matching. So we need some more predefined functions in addition to the ones that we already have. So plus, minus, map, plus, plus, and whatever. So what are the additional functions that we need? So we need one function to represent undefined values. So we need a function bot which is undefined everywhere. So we need a function bot which is undefined everywhere. Now this function we could also implement in simple Haskell. That's no problem. For example, we could implement it like this. We would say bot is of type A, and then the definition is bot equals bot. Now, so if we like to, we can implement this, and we don't really need this as a predefined function. We could extend every program by this additional declaration later on, and then this is already simple Haskell. So that's not a real problem. But to make things easy, I don't want to do this and extend the program all the time. I will just say, let's have one more predefined function, bot, and it could be defined like this. This is simply undefined always. Now the next function is something you cannot define without pattern matching. If you have pattern matching, you can define all these functions that I now present. You can easily define in full Haskell if you have pattern matching, but you cannot define them if you don't have pattern matching. So we need another function which is called is a constructor. So for every constructor, we need a function is a, and this function is meant to recognize whether the argument is defined with this constructor or is not defined with this constructor. So the meaning is we need this for every data constructor, constru, and the idea is this function should recognize whether the argument is built with constru or not. So has to find out whether its argument is built with the constructor constru. So, for example, assume we have the data type list again. So we define this ourselves. So lists are either empty, represented by the data constructor nil, or they are not empty, and then this is represented by a data constructor cons, which takes two arguments, one of type A and one of type list A. And now we would need a function is a nil and is a cons. Is a nil checks whether the argument is nil. Now that's not very difficult and can also be defined without pattern matching. But is a cons is already a bit more problematic. In particular, if you have more than just two constructors, this is very problematic. So you would have something like is a cons would look is a cons. You could define this as follows in Haskell. It would take a list and it would give you back a Boolean, and it would be either true or false, depending on whether this is built with cons or this is not built with cons. So the definition would be like this. If this is built with cons, so it has the form cons xy, then the result is true. And otherwise is a cons nil, the result is false. And now for this data structure, you could still define this without pattern matching. You would simply ask, is your list nil or not? If it's nil, you return false. If it's not nil, you return true. But if you have 3 data constructors, then you are in trouble. So this in general, this cannot be defined without pattern matching. And so if you want to, and therefore we have to include it as a predefined function. We cannot just define this ourselves in simple Haskell. Now this is not simple Haskell because first of all we have 2 declarations, and second, here we have patterns. So this is not a variable, these are patterns. And in simple Haskell you may only have 1 declaration. There may not be any arguments, you need a lambda, and this lambda may only have variables as arguments and not patterns. So here we have pattern matching, and that's not allowed. Now, the next predefined function that we need is similar to this one. If you know that an argument is built with a certain constructor, then you need a function which extracts the argument of this constructor. This is called arcof. And for example, if you know you have an object built with cons, then arcof gives you the 2 arguments of cons. Again, this is no problem to define this if you have pattern matching, but you have no pattern matching, that is rather difficult. Okay, so the next function is called arcof, and we need this for every data constructor constru. And what it does, it returns the tuples, returns the tuple of constru's arguments if the argument of arcof constru is built with the data constructor constru. So how would this work for our example up there? So arcof cons, you can define this in Haskell if you have full Haskell. What it would do is it takes a list, and if this list is built with this constructor, cons, then it gives you back the 2 arguments of cons. Now the 2 arguments of cons have this type. The first one has type A, the second one has type list A, so it gives you back a tuple of something of type A and something of type list A. And, well, if you have pattern matching, it's not a problem to define this. You can simply say this. So if your argument is defined with cons, you get x, y. If not, then this is not defined. So basically, what these 2 functions do is they can recognize if an argument starts with a certain constructor. That's the meaning. That's what this is good for. And they can extract the arguments of this constructor. This is what this is good for. And this is essentially what pattern matching is good for. Pattern matching can, on the one hand, make sure that, well, certain declarations are only executed if the arguments start with certain constructors. And moreover, you can, by putting variables into your patterns, you can make sure that these variables are assigned the values of the arguments of the constructor. So you can, in this way, extract the arguments of a constructor. And to mimic this behavior, we need this arcof. Now, in the same way as we need this for constructors, we need it also for tuples. So now we get 2 more functions, something like isA for tuples and something like arcof for tuples. and that's all. So these are the predefined functions we need. So for tuples, the isA function is called isA n tuple. IsA n tuple, and n is a number 0 or 2, 3, 4, 5, 6, and so on. And what this should do is, so for every n natural number except 1, because tuples with one component we do not need. Tuples with one component are the same as just the component itself. And what they should do is they should simply find out whether the argument is a tuple of n components. And if so, they return true. So this has to find out whether the argument is a tuple of n components. Now again, in Haskell, if you have pattern matching, it's not a problem to define this. So again, this is impossible without pattern matching. And the same is true here. So how would you define this in Haskell? Well, this would be a function which works for any tuple of n components of arbitrary type, and it returns a Boolean. And the definition would be like this. If the argument is really a tuple, then the result is true. Otherwise, it's undefined. Now, this function does not always return true, because if here you have something which is completely undefined, so something whose semantics is bottom, then the semantics of isA n tuple applied to this stuff will also be bottom. So, for example, if you apply isA n tuple to bot up there, then semantics will be undefined. Or if you implement it in Haskell, it will not terminate. It will not give you true. And then finally, we need something like arc of. So if we have a tuple of n components, we need to be able to extract every component from this tuple. So we need a kind of selection function, which, if you have a tuple of n components, gives us component 1, component 2, component 3, and so on. So we need some function cell ni, and this selects the ith argument or the ith component of a tuple with n components. So in Haskell, let's make one example. If you want to, for example, define cell 3, 2. So this takes tuples with 3 components and gives us component number 2. So the type would be, you take tuples with 3 components of types A1, A2, A3, and you want the second component back, so the result will be of type A2. Well, and the definition is easy if you have pattern matching. You would say, I take this tuple, x1, x2, x3, and I return x2. But again, if you have no pattern matching, then you cannot define this. So these are new predefined functions that we will add to the initial environment. So when we now define the semantics for a complex Haskell, our initial environment will contain a few more functions, namely these ones. And that's it. That's enough to define the semantics of any complex Haskell program. Now let's again repeat this formally. Okay, so definition 228 should be the new predefined functions. Predefined functions. So if we have a complex Haskell program, then we can say how these predefined functions look like. And they're just finitely many, because if we later on want to do something automatic, then it's nice if we just have finitely many predefined functions. So we don't need them all. Well, is on Arcov we need for every constructor in the program. Now, if your program is finite, there are only finitely many data constructors in this program. So for a Haskell program with the constructors con, and now we only need is on Arcov for the constructors in con. Now for tuples, in principle, of course, is a n tuple you might have for every n, for every natural number. And similarly, selection functions you might also have for every n. But we don't need them for every n. Because if you have your program fixed and your program is finite, then you can be sure that only tuples up to a certain size will occur in this program. So maybe you need tuples up to 10 components, but then you won't need tuples with 11 components. So there's a limit on the maximum size of tuples that you will ever need. And this limit can be computed as follows. This limit is k. So this k is the maximal size of tuples that can occur in the transformed program. So your program will be transformed, and in this transformation will create tuples. And it may create tuples which have more components than the tuples in the original program, but there's a certain upper bound. And this will be the maximal size of tuples that can occur when transforming the program. So how can we compute this? K is the maximum of the arities of all functions in the program. So if you have a function of arity 3, then there can be tuples of arity 3 later on. The arities of the functions in the program. Then, of course, if in your original program you already have tuples of length 10, then in the transformed program you will also have tuples of length 10. So this should be the maximum of the arities of the length of the tuples. The length of tuples in the program. And the number of declarations. So if you have a complex Haskell program, you may have many, many declarations. And it can happen that you create, during the transformation, new tuples which have as many components as you have declarations in your original program. And the number of declarations. And the number of declarations in the program. So how k looks exactly like, that's not very interesting. The only interesting thing is k is finite. So you only need these predefined functions. You only need finitely many of these predefined functions. Then we need the following predefined functions. Predefined functions. So the predefined functions are the ones that I just mentioned. So it's a function bot of type A. It's a function is a constructor for every. Oh, it is a constructor has the following type. It takes a type and it gives you back a Boolean. And you need this for every constructor of con. So con are the constructors of your Haskell program, and if constr is the constructor of con, then you need this is a function. And if const is a constructor of con, then it has a certain type. So let's say this constructor has the type, a function from type 1 to type 2 to type n to type. So this constructor is a constructor of this type over here. And the is a function takes objects of this type and then checks whether they start with this constructor or not. And if they start, it returns true. And if they don't start with this one, it returns false. And now arc of is similar. It takes objects of this type and then returns the tuples of the arguments. So a tuple type 1 to type n. And here, now this has to be copied. And then we need these things for tuples. So is a n tuple goes from, you take n components and you return a Boolean. And we need this not for all n, but only for n's up to k. For all n from 0. For 1 we don't need it, but for 2, 3, 4, until k. And then finally we need the selection function. And this should take such a tuple and give us the ith argument. And this also we need for all n in here and for all I between 1 and n. So these are simply new names for functions, and we have given their types. And now the initial environment has to be extended, and it has to assign the right semantics to these predefined functions. And now this extended environment I will not call omega, but omega with an index tr for transformation. This is the initial environment we need when we transform functions. So the initial environment omega is extended to an environment omega tr, which stands for transformation. So the semantics of the previous predefined functions is as before, but now these new predefined functions have a predefined semantics as well in this omega tr, where the new predefined functions have the following semantics. Okay, and it is as follows. So what would be the semantics of bot? So bot is a variable, but this variable has a predefined semantics, and the predefined semantics should be the always undefined value. So it should be this thing here. So just like for the other predefined functions, we now have to add some more, and we will need this in order to transform complex to simple Haskell. What is the semantics of this? Is a function for constructors in omega tr. Well, it's a function. So it takes an object, and now it checks whether this object is built with this constructor constr. And if so, it returns true. So this returns true in construction 0, in DOM, if this thing is built with this constructor. Now, how do objects look like in DOM when they start with this constructor? They are tuples, and the first component of this tuple is constru. So if D is of the form first this constructor and then something else, D1 to Dn, in constructions n in DOM. Now it returns false in construction 0 in DOM. If this is also built with some constructor, but not with the same constructor. So if D is built with some constructor prime, and then D1 to Dm in constructions M. Constructions I abbreviate to constru in DOM. And this constructor prime is not the same as the constructor that we look for. And otherwise we return bottom. Now, what's the semantics of arc-of? Arc-of works very similarly. So the semantics of arc-of is also a function which takes some object D, and if this object is built with this constructor, then you get back the tuple of the arguments. So you get back D1 to Dn in tuples n in DOM. If D really is built with this constructor, and then you have D1 to Dn in constructions n in DOM. Otherwise you get bottom. And now we have something similar for the tuples. So what is the semantics of is n tuple? Well, this is a function which also takes an object, D, and it checks whether D is indeed a tuple of n components. And if it is, then it returns true in construction 0 in DOM. Now I abbreviate this. If D is indeed a tuple of n components, so D1 to Dn in tuples in DOM. And otherwise you get bottom. And the final case is the cell function. So cell ni, it takes also an object D. And if this looks like this, then it returns you the ith component. So it gives you di if D is D1 to Dn in tuples in DOM, otherwise you get bottom. Otherwise. Okay, so now we have defined these predefined functions, and we have said that now we have an initial environment which also assigns a certain semantics to these predefined functions, and the semantics does what you would expect. Now, before I define the transformation from complex to simple Haskell, let me make precise what I mean by complex Haskell. So I will still not regard completely arbitrary Haskell programs. I will still make some restrictions to make life easy. So what we have is full Haskell is still more than what I will now call complex Haskell. Now most of the things that are in here but not in here are harmless, And you can easily extend the transformation from complex to simple Haskell to most of the constructs in here as well. So for some of the constructs, we will do this in the exercises. There are some where it is not easy, but for most of them it's easy, and I just don't do it to save some time. The step from complex to simple is much harder. Now, and as I said, there are also some things which are smaller than simple Haskell, the lambda calculus and the pure lambda calculus, but we will do this later. So what is complex Haskell? Or more precisely, what is the difference between full and complex Haskell? So, a complex Haskell program is a Haskell program so now we have all the restrictions. So again, no type synonyms. Without type synonyms. So some declarations which start with type. Now this is no real restriction. This is just an abbreviation. For example, instead of list of characters, you can write string, but this is just syntactic sugar. So you can immediately transform your program and eliminate all type synonyms. So this is no real restriction. This here is a real restriction without type classes. So this is a real restriction. Let me write restriction here. This is a real restriction. If we want to include type classes, this will make life much more complicated. And therefore we exclude it. Then we don't regard infix declarations. Now this is no real restriction. You can immediately transform every infix function to a prefix function by simply writing brackets around it. This is just notation. So to make life easy, we will avoid looking at it. We don't have predefined lists. Now this is also no restriction because instead of predefined lists, you can define lists yourself. So you can immediately pre-process your program and throw out the predefined lists and replace them by lists which you define yourself. Then we require that the program is sorted in such a way that the defining equations for one function follow each other. So you may not first have one defining equation for plus, then one for times, and then one for plus again. So this is just a sorting. And if this is not sorted, you can sort it immediately. So again, no real restriction. Defining equations for one function have to be beside each other or have to follow each other. So this is no restriction. Then pattern declarations. In Haskell you can write things like xy becomes 2, 3. Now this we don't allow. We only allow pattern declarations where on the left-hand side you have just one variable. Now obviously that's also not a big restriction because it's very obvious how to transform this into pattern declarations where on the left-hand side you have just a variable. You can replace this by x equals 2 and y equals 3. But to make life simple, we will assume this. So pattern declarations only have a variable on the left-hand side. A variable on the left-hand side. So this we do not allow. Again, that's not a big restriction. Then we have no where. So local declarations with where we do not have, but we have let. So this is also no real restriction because if you have something with where, you can immediately transform it into a declaration with let. we have no conditional right-hand sides. No conditional right-hand sides, but we have if and we have case, and therefore this is also no restriction. So we may not have something like maxi of x comma y. If x is greater or equal than y, then we return x, and otherwise we return y. So something like this is not allowed. So this notation with this vertical bar is not allowed. That's not a big restriction because it's obvious how to formulate this in a different way using if then else. And if then else we do allow. So this is just to ease the treatment. Now let's see, anything else? Yes, one more restriction. The patterns that we use may not contain plus and they may not contain the at symbol. So no patterns with plus or at. Now this at is strange anyway, these patterns with at. You can immediately transform this into patterns without at. And this plus, these are patterns for integers, so something like a pattern x plus 1 or x plus 2. This you can also transform easily, and moreover, it is highly doubtful whether these patterns are a good idea for programming, and the people who design Haskell are heavily discussing whether to throw out these patterns at all from Haskell. So currently they are still in there, but maybe they will be thrown out of Haskell anyway. But it would be no problem to include this as well. So the only real restriction is this one. Everything else, you could easily extend the transformation to simple Haskell to these other things. It will just make life a bit more, not more complicated, but more definitions and even longer. So I drop these to make life easier. I don't regard all these things. This one would be really hard. The rest is not hard. And so after we now know what we have to do, we can start. So this transformation will work as follows. Transformation. So for the transformation, I will give 12 rules. And these 12 rules you can apply to a complex Haskell program. You can apply them in any order. So if one of the 12 rules is applicable, you can apply it. It can happen that many of these rules are applicable. Then it is up to you which rule you apply. You can apply them in any way you like. And then after a while, you cannot apply any of these rules anymore. And then what you have got is a simple Haskell program, which is equivalent to the original one. So 12 transformation rules, which may be applied repeatedly and in any order. And their application will always terminate, and it will always give you a simple Haskell program. Now for the transformation, the data structures are important because they give you the constructors. And therefore they determine how the predefined functions look like. They determine whether we need is-a construct and arc of construct. That's the only thing they are used for. So data structure declarations in your original program, in the program, they are needed to determine the predefined functions. The predefined functions, so things like is-a constructor and arc of constructor. But apart from that, they play no role. So we do not regard anything that has to do with typing. We assume that our program, our complex Haskell program, is well typed, and then we do this transformation. Apart from that, types are not regarded in the transformation. So what the transformation does actually is, if the original program is well typed, then the resulting program is well typed as well. And if the original program is not well typed, then the transformed program is also not well typed. And that means we can use this transformation also for type checking. We can then instead type check the resulting simple Haskell program, and if this is well typed, then the original one is also well typed, and vice versa. So original program well typed is well typed if and only if the transformed program is well typed. Okay, so how do these transformations look like? Let me start with giving you the first 2 or 3 transformations, and they are easy, and then you get a first idea how they look like, and we do the remaining rules in the next lecture. So what we do is we start with a complex Haskell program, and our goal is to get a simple Haskell program. So simple means we may have only one single declaration, and the single declaration has this form. So there's just a variable on the left-hand side. And moreover, we have no pattern matching. So let me try to illustrate this with an example. Here is an example for a natural-looking complex Haskell program. So this complex Haskell program computes append. So it's a program which concatenates 2 lists, and I use the user-defined lists with nil and cons. So this works as you might expect. If you want to append the empty list to the list Z, you get Z. If you want to append a list starting with cons, so this is the list where the first element is X, and Y is the rest of the list. If you want to append this to Z, you get a list which starts with X, and then append is called recursively with Y and Z. Now, this is not simple Haskell because of many reasons, and the first reason is you have many declarations here. So this is something which is not allowed in simple Haskell. So the example append. So we can see, first of all, we have many declarations, and second, in simple Haskell, on the left-hand side, you may only have a variable. But here, on the left-hand side, you have not a variable, but append is applied to several arguments. So you have append and then 2 patterns, nil and Z. Now, that's not allowed. So the first problem is we have more than one declaration. And we have not just a variable on the left-hand side. Now, how can we transform this program into a program which at least solves these 2 problems? So we want to have just one declaration instead of 2, and we want just one single variable on the left-hand side, and not something like append nil Z. So basically, you want something which starts with append and then equals, and then something on the right-hand side, and just one single declaration. Now, how can we do this in Haskell? So let's reformulate append with just one declaration, and append is on the left-hand side, nothing else. Any suggestions how to do that? Now, the only way to get rid of arguments is using lambda. So if you want to use lambda, then it will somehow look like this. Now, this already solved problem 1. This solves the problem how to get rid of the arguments of the left-hand side. Now, on the left-hand side, we have just append, and then on the right-hand side, we have some expression which starts with lambda x1, x2. So basically, append is a function which takes 2 arguments, x1 and x2. Now, how can we now get these 2 declarations into just one? Any idea how to? Yeah. Now, that's very, very clever, because this is indeed what we will do in the end. So that's very good. That's what we will do. If we use is a nil and is a cons, we have solved all the problems. Now, we will not go as far as this here, because this rule that so there will be a rule 1, and in our example here, the patterns are built with constructors. And in order to get rid of this pattern matching, we do exactly what you just said. We will, in the end, use is a nil and is a cons to recognize this. But in general, patterns can, of course, look differently. Patterns can also be tuples. And in order to handle all these cases together, the first thing that we do is we use case. And then later on, we get rid of this case. And then depending on how the pattern looks like, we use is a nil and is a cons, or we might use is a tuple. Oh, this was a very clever answer, but not the one that I expected. So it was better than the one that I expected. And so as a first step, let's just do this, and then later on we continue. Because, I mean, people can also write expressions with this case construct anyway, and we have to transform this as well. So in order to save energy, we will then introduce a rule to get rid of this case construct. We need this anyway, but we transform this into case first. Now, what is case? The case construct, if you don't remember what it does the following thing. Here, you have a pattern. And you then check whether your actual arguments matches this. If it matches this, the result will be Z. If it doesn't, you check whether it matches this one. If it matches this one, the result will be cons X append YZ. So let's reformulate this as a general rule. And these rules I will denote like this. So this is rule 1. And what rule 1 does basically is it transforms function declarations into pattern declarations. Transform function declarations into pattern declarations. So, and these rules I will denote as follows. I will write the stuff that I start with. So if we have something which looks like this, a first declaration where this variable is something like append. So if this is applied to pattern 1, until pattern 1n, and then you have another declaration where this variable is applied, this equals expression 1. If this is your first declaration, and then you have many more declarations for the same variable, so pattern k1 until pattern kn equals xk, then you can transform this into the following declaration. So the meaning of this is we write rules like this. First, some part of your program that you had before, then a horizontal bar, and then the thing that you can transform this into. So this thing can be transformed into this thing. The thing that is above this line can be transformed into the stuff that is below this line. So you can transform this into just one single declaration of this form. Var is a function which takes n arguments, x1 to xn. And then if x1 to xn, if this tuple x1 to xn has the form pattern 1 until pattern 1n, then the result is x1. And otherwise, you take the next pattern, and finally, you take pattern k1 and pattern kn, and here the result would be xk. And here, of course, x1 to xn are new variables. So variables that don't occur in your program yet. You only do this if you need it. So if n is greater than 0. If n is 0, then this is already a pattern declaration, so there's nothing to do. And moreover, this sequence of declarations is maximal. So suppose you have 3 declarations for var, then you have to apply this to all 3 declarations, not just 2 of them. So the above sequence of var declarations is maximal. So in other words, there are just k declarations for. So there are just k declarations for var in the program. And now this rule allows you to transform the original append program into this. And now, of course, we have not solved our problem yet because we still do pattern matching here, and how to get rid of this pattern matching we will then discuss on Tuesday. Okay.